Hi and a good day, everyone. So in this video, we will be talking about fracture mechanics. I will give you some introduction to fracture mechanics. All right. So when we talk about fracture mechanics, what do you know about it? What does it mean by fracture mechanics? Actually, fracture mechanics is the discipline that concern with the behavior of materials that are containing cracks or other small flaw. And when we mention the term flaw, it refers to such features as a small pore or holes on the surface or micro crack. Yeah. Right. So in fracture mechanics, what we want to know is the maximum stress that a material can withstand if it contains a flow of a certain size and a geometry. The fracture toughness measure the ability of material that containing a flow to withstand and applied loading. And here we have some issues that we can relate to this chapter. The first one is how the cracks can lead to failure. How do we quantify fracture resistance? How do the fracture resistance differ for different types of material? And we also be discussing about estimation of stress to fracture, and also the loading rate, the loading history, and the temperature effects on the material's behavior. So what does it means by fracture mechanics? So the fracture mechanics refers to the mechanics of solids that containing cracks with special attention to their growth. Fracture mechanics is a failure theory that for the first one is determine material failure by energy criteria, possibly in conjunction with a strain or yield criteria. And secondly, we consider failure to be propagating throughout the structure rather than simultaneous throughout the entire failure zone or surface. So now we will be discussing some importance of fracture mechanics. Fracture mechanics is very important, especially for the first one is in terms of the selection of a material. So let's say we know the maximum size A of flow in the material and also the magnitude of the applied stress. And then we can select a material that has a K sub C that is large enough to prevent the flow from growing. So K sub C is a fracture toughness. And also in terms of design of a component, so let's say that we know the maximum size of any flow and the material, and therefore its K sub C has already been selected. We can calculate the maximum stress that the component can withstand. And then we can size the part appropriately to ensure that the maximum stress is not exceeded. And also, if the materials has been, let's say, has been selected, the applied stress is known, and the size of the component is fixed, and then we can calculate the maximum size of a flow that can be tolerated. A non-destructive testing technique that detects any flow that greater than this critical size can help to ensure that the part will function safely. And also, any crack or imperfection limits the ability, for example, let's say we have a ceramic to withstand a tensile stress. And this is because the crack that sometimes that we call as a Griffith flaw will concentrate and magnifies the applied stress. And we will be talking more about this in the upcoming slide. So how do we define fracture? Failure, as we already know, is the state or condition of not meeting a desirable or intended objective of the object or material. On the other hand, a fracture is the separation of an object or material into two or more pieces under the action of applied or induced stress. So how does a fracture differs from a failure? We can say that a failure is the state or condition of not meeting desirable or intended objective of the object or material. On the other hand, fracture is the separation of an object or material into two or more pieces when we apply stress to that particular material. And damage will lead to failure, and a failure will finally lead to a fracture. So here we can see the relationship between failure and how damage will lead to failure, and subsequently failure will lead to the fracture of material. So when a crack is present in a material, there is a critical stress that must be exceeded in order for a crack to grow. Yeah, and the level of stress required is defined by the amount of work that must be done for a crack growth. And this level of work is referred to as the material toughness, or G sub C. So when we have a crack that present in material, the crack tip stress, or sigma sub m, should be larger than the sigma sub c, or critical stress, in order for the crack to grow. So material toughness, G sub c, we can say it as an amount of work that required for a crack growth. Yeah. All right. So when a G sub c is low, a low G sub c indicates that a crack growth is easy. For example, such as in glass or cement material. And when we have a high G sub c value, this high value indicates that the crack growth in the materials is difficult, such as in materials such as a copper or a plastic composite. So we can say that when we have low G sub c, the crack growth is easy, and when we have a high G sub c, the crack growth is we consider it as difficult compared to materials with a low value of G sub c. How do we define fracture mechanics and fracture toughness? Fracture mechanics is a methodology that used to predict and diagnose the failure of a part with an existing crack or flaw on the surface or within or in the within that material. And the presence of a crack in the part magnifies the stress in the vicinity of the crack and may result in a failure prior to that predicted using traditional strength of material method. On the other hand, we have fracture toughness. That is the resistance of a material failure in the presence of a flaw. A material can resist a stress that we apply up to a certain intensity, applied stress intensity up to a certain critical value above where the crack will grow in an unstable manner, and failure will occur. And this critical stress intensity is the fracture toughness of the material. The fracture toughness of a material is independent on many factors, including environmental temperature, environmental composition, the loading rate, the material thickness. In terms of material processing, it will also affect and also the correct orientation to grain direction. All right, so now we will be talking about failure modes in a material. So we can, there are three primary modes that define the orientation of a crack relative to the loading. A crack can be loaded in one mode exclusively, or it can be loaded in a combination of mode. For example, here we have three types of failure mode here. The first one, in mode 1, we have an opening where displacement is normal to the crack surface. And in the middle here, we have a sliding mode or in plane shear, where the displacement is in the plane of the plate. And the third one, we have mode 3, that also known as a tearing mode, where the out of a plane shear will happen. Right, so the process of fractures can be divided into two general components. The first one is we have a crack initiation, and secondly we have a crack propagation. And remember that the two categories of fracture are the ductile fracture and brittle fracture. If you remember from our previous discussion, what are the characteristics of a ductile and brittle failure? We know that ductile fracture, it comes with a significant plastic deformation, and on the other hand, for a brittle fracture, it comes with little or even no plastic deformation, and it is catastrophic in nature. So now we will be talking on some fundamental of stress concentration. So prerequisite for crack propagation is that the stress at the tip of the crack must exceed the theoretical cohesive strength of the material. Yeah. So basic stress analysis, we assume that the components are smooth, have a uniform section, and also has no irregularities. But in practice, virtually all the engineering components have to have changes in section and or shape. Okay, let's say we have two examples here. If you look at this figure, we can see that the flow of stress is smooth in figure A. But because of the existence of we have a fracture on the surface, we can see that there is an interruption in the stress flow line here. We can see that more stress are concentrated at the tip of the crack. So any discontinuity, the changes, the stress in terms of the stress distribution within the vicinity of the discontinuity, so that the basic stress analysis equation no longer apply. Yeah, and such discontinuity or a stress raiser will cause a local increase of stress that we refer to as stress concentration. Right, so just want to give you one example of stress concentration that we encounter almost daily. Just imagine the stress concentration is the notches on the edge of our candy wrap. Yeah, so without the notches, without the notch, it is almost impossible to rip open the candy wrap with a bare hand. Yeah, quite impossible for us to rip open the candy if we don't have notches here. And what does this notch do? It will amplify the stress on a very small area on the edge, and thus will induce a failure on the wrap. And this is one example of stress concentration in action. All right, so now we will be talking about a notch, or the term in Bahasa Melayu is a taku. We will be talking about a notch sensitivity. Yeah, so we can define the notch sensitivity as to what extent is the sensitivity of a material to fracture is increased by the presence of a surface inhomogeneity, such as notch, a sudden change in a section, and so on. And a low notch sensitivity, we usually associate it to ductile materials. And on the other hand, we have a high notch sensitivity that we usually associate to brittle materials. So, what is actually a crack? Yeah, so a crack is actually a localized breakdown of bonds in material. It could be internal or scratch on the surface. Yeah, so a crack will form in material either inside or on the surface, as as we can see in the figure here. Yeah, we can see that the crack will form in the material. It can form on in either inside, internal, or on the surface. And we have to remember that the cracks in materials under loading are a stress concentrator. A stress concentrator is any discontinuity that will amplify and apply stress. So this is the definition of a crack. We can define crack as a localized breakdown of a bond in a material. It could be internal, inside that particular material, or on the surface. And we have to know that the stress cannot be transferred to the crack, and therefore stress is concentrated at either side of the crack. And the transition from that slow, stable to the fast and unstable phase will happen when the crack becomes critical or when it reaches a critical length. Yeah. Right. So we move on how do we quantify a crack. So let's say that we have materials and we apply a stress to it, a sigma naught. Yeah. And let's say that inside the materials we have a crack, like what we can see in the figure. And we are going to generalize the shape of the crack as an elliptical crack, like this. We generalize the shape of our crack here as an ellipse. And at the tip of the crack, we have a small circle to show the sharpness of the crack. And the radius of a curvature that we call as rho, yeah, the radius of a curvature that we call as a rho. And if the radius is small, then we call it as a sharp crack. But if the radius is quite large, we call it a blunt crack. Yeah. And also, we can also quantify the length of the crack as a 2a. Yeah, we quantify the length of the crack as a 2a. And from all these values, we can quantify the stress concentration factor. The K sub T is equal to the maximum stress at the tip of the crack. Yeah, the K sub T is equal to maximum stress at the tip of the crack divided by the applied stress, and that is roughly equals to 2 times a square root of half length of the crack divided by the rho, or the radius of curvature. And this one for sigma max is the maximum stress at the tip, and for sigma naught is the applied stress. So here we have a typical plot that's showing the growth of a crack. We notice that the crack will initially grows very slowly. Yeah, the crack will initially grows very slowly, but the growth will accelerate as the crack size increase. And the reason for this acceleration in growth is that the growth rate is dependent on the stress intensity factor at the crack tip. And the stress intensity factor is dependent on the crack size, A. As the crack grows, the stress intensity factor will increase, and this will lead to a faster growth. And the crack grows until it reaches a critical size, and failure will happen. So we can characterize the process of failure by the first one is the crack initiation. And then we will move on to crack propagation, where the crack advances incrementally with each stress cycle. And subsequently, we will enter the final failure, where it occurs very rapidly once advancing crack reach a critical size. We know that the fracture stress depend on the crack size, and we also know that the fracture stress depend upon the material property such as stiffness. And the first person to establish a quantitative relationship between fracture stress and the crack size and stiffness was a scientist named Griffith. Griffith attributed the discrepancy between the observed fracture strength of a crystal and the theoretical cohesive strength to the presence of flaw in a brittle material. And this theory is only applicable to perfectly brittle material such as glass. And we cannot use this theory directly to metal. So we consider a wide sheet of unit thickness of a brittle material. It has lanes shape, crack of 2C or 2A here, length, which runs from the front to the back face as illustrated in the figure. So when we have longitudinal tensile stress is applied, the crack will tend to increase in length in the transverse direction. So when the crack spreads, the surface area of the crack will increase. In short, we can say that any crack or imperfection will limit the ability of that particular material. For example, we have a ceramic to withstand a tensile stress that we apply. This is because the crack, or sometimes that we call as a Griffith flaw, will concentrates and magnifies the applied stress. So when a crack propagates, the elastic energy release in a volume of materials, and the two new surfaces will be created. The crack propagates if elastic strength energy release is higher than the surface energy. So a crack or imperfection will limit the ability of a ceramic, for example, to withstand the stress that we applied. This is because the crack will concentrate the applied stress. Flows are stress concentrators, and the stress will be concentrated at the crack tip. Yeah, so it is if it is assumed that a crack is similar to an elliptical hole through a plate, N is oriented perpendicular to the applied stress. The maximum stress, sigma m, it will occurs at the crack tip and may be approximated by equation that we can see here. So this is the Griffith crack model, and this is the equation where the rho sub t is the radius of curvature at the crack tip, and then we have sigma sub naught is the applied stress, and then we have sigma sub m is the stress at the crack tip. So these flows are detrimental to the fracture strength because an applied stress may be amplified or concentrated at the tip. The magnitude of this amplification depend on the crack orientation and also the geometry. This phenomenon is demonstrated by the figure here. We can see that we have stress profile across a cross section that containing an internal crack. So as indicated by this profile, we can see that the magnitude, we can see that the magnitude of this localized stress diminish with the distance away from the crack tip. So when we try to design a path, it is important for us to avoid a sharp corner. Yeah, because we want to avoid a stress concentrator by avoiding a sharp corner. So how do we achieve that? Okay, we can avoid a sharp corner by adding fillet to our path. Yeah. So the sharper the fillet radius, the more stress concentration that we have, and eventually this will lead to a failure. So here we have a stress concentration factor K sub T. We have a stress concentration factor K sub T. It is a dimensionless factor that is used to quantify how concentrated the stress in a material.